Hello, this is Mahandra Didiya. This is the second related video in the fourth module in the book on liquid formulation. This module focuses on physicochemical characterization of emulsion. The second related video is on type and classification of emulsions. The orientation of emulsifier at the interface plays critical role in the type of emulsions. The type of emulsion depends on emulsifier's hydrophilic and lipophilic properties and the volume fraction of both phases, oil and water. In oil and water, dispersed phase is oil and continuous phase is water. Emulsifier's orientation is shown here. The lipophilic part is inward at the interface, and that's miscible in oil portion of the emulsion. In water and oil emulsion, dispersed phase is water, and the emulsifier's lipophilic portion is outward at the interface, as shown here. Emulsifier's hydrophilic, lipophilic properties, volume fraction of both, and the orientation of emulsifier at the interface dictates what kind of emulsion it would be, whether it would be oil and water or water and oil. So classification of emulsion, most commonly known are water and oil emulsion, generally designated by WO, aqueous system that contains water. It may have other ingredients that are soluble in water. Oil and water emulsions are designated as OW. Dispersed phase in WO, water and oil, is globule of water, and continuous phase is oil. Water and oil, dispersed phase is a globule of oils. Continuous phase is water, aqueous solution, in which the dispersed phase of oil globules are suspended. Double emulsion or emulsion of an emulsion. This is characterized by coexistence of an emulsion within an emulsion. And we'll look at details. In this case, the dispersed phase itself is an emulsion. It can be oil and water emulsion or water and oil emulsion. So it contains either oil and water or water and oil emulsion. The continuous phase can be different. It can be water for water and oil emulsion, WOW, in which the dispersed phase is water and oil and generally designated as W1 to distinguish it from a W2 continuous phase. W1 is also called inner or core phase, and O here is called a shell phase. OWO, to make it easier to see which was inner and outer, designation 1 and 2 are used. Oil, outer O2 is a continuous phase in which oil and water emulsions are suspended. O1 is also referred as inner or core phase, and in this case W will become a shell phase. In addition to that, siloxane, which has an oil-like properties, is also extensively used in both cosmetic and pharmaceutical products. In this case, double emulsion would be OWS, oil and water emulsion suspended in siloxane, which are also called silicone oil. O in this case inner or core phase, W is a shell phase. The shell phase is immiscible with the surrounding phases. So oil in this case is immiscible between the water phase. Water phase here is immiscible with the two oil phases, and water phase is immiscible with oil and siloxane. In addition to that, there are water and siloxane emulsions. What the structures look like from a physicochemical characterization perspective. Emulsion. The dispersed phase is composed of small globules. Shown here, water phase is a continuous phase and oils dispersed and stabilized by the use of surfactants or emulsifiers. Water and oil has oil as a continuous phase and water is a globular phase. And the interface orientation of surfactant, as pointed out earlier, lipophilic portion is embedded in oil and the hydrophilic or water-loving is oriented towards the globule of water. Hydrocarbon tail and polar heads come in many configurations. Double emulsion contains an emulsion, in this case shown as an water and oil emulsion, in a continuous phase. It could be multiple globules of water surrounded by shell phase dispersed into the continuous phase. Water, oil, water emulsion contains globules of different size and different characteristics in the continuous phase, in this case water. Oil, water and oil, the double emulsion contains, this is the droplet that contains emulsion. Oil and water are dispersed in a continuous phase. This is a double emulsion, emulsion of an emulsion. The double emulsion showing you water, oil and water, and this is applicable to all types of double emulsion, has two different interfaces. And here idealized interface is shown. Yellow is oil and blue are two different water phases, W1 and W2. In an idealized interface, the water in oil, the surfactant will orient in such a way that it covers the inner emulsion only. Oil and W2 continuous phase will have emulsifiers specifically designed so that they orient their structure, shown here as a black dot, orients only in W2 phase. In reality, green surfactant or emulsifier may also orient in the W2. Similarly, black shown here, emulsifier will orient towards W1 inner phase water. Oil phase here is immiscible with either of the water phases. Oil, water and oil, water and siloxane can be similarly presented but are not shown here. Let's look at what double emulsion looks like. Double emulsion formed at a different rate, and you will see the rate of formation, higher rate and the slowest rate here. And you'll notice this is a double emulsion, this is a continuous phase. And emulsion is incorporated in here. And you'll notice that it can have multiple core phases. In this case, you will see it's the rate of flow. So you see that rate so we looked at classification based on oil and water, water and oil, and double emulsion. We now look at classification of emulsion based on droplet size. It is extremely important to understand the stability of emulsion depends on the droplet size. So when we make double emulsion, the internal emulsion is always sub-micron size emulsion. Macro emulsion, which we traditionally call emulsion or classical emulsions, their droplet size exceed in micrometer and they are produced by simple mechanical agitation. Nano emulsions, emulsion droplet size or globule size can be reduced to less than 500 nanometer, generally between 20 to 500 nanometer. This requires additional energy, or it can be done by self-assembly inversion method. Microemulsions are these pseudo single phase. They behave like monophase system, and the emulsifier and surfactant make it possible to coexist at a molecular level. Microemulsions have dynamic microdomain which are not necessarily spherical, and they are 10 to 50 nanometer, range being 1 to 100 nanometer. And microemulsions, because they behave like monophasic, they are thermodynamically stable for longer duration. Droplet size appear several particle size, in this case shown as 50 micrometer. Nanoemulsions are generally homogeneous. Both, they are not as stable. They are made with high and low energy methods. Energy needs to be very high. And polydispersity, the different particle size. Macroemulsions are polydispersed. They have a wide variety of particle sizes. Nanoemulsions typically have narrow particle size distribution as shown here. Microemulsion formation requires proper oil to water ratio and surfactant and co-surfactant ratio. In the phase diagram, it's shown here as oil and water microemulsion and water and oil microemulsion. When we make microemulsion, we need to understand the relationship of surfactant and co-surfactant and water and oil ratio. So what do they look like? Classical emulsion produced by mechanical energy looks creamy. Nanoemulsions produced by high energy or mechanical self-assembly inversion. And you can see the green lines here, much clearer than macroemulsion. Microemulsions are pseudo monophasic system. They behave like solution. They appear like solution, so you can see microemulsion here. And the green lines drawn on the black background are clearly visible. So surfactants and emulsifiers are important in microemulsions. Segregation of phases and breaking of emulsion. Gibbs thermodynamic theory would say that emulsion is thermodynamically not stable and it will eventually separate. When we are designing emulsions, we are looking at kinetic stability over time frame. The kinetic stability of emulsion, because they are suspended particles, Stokes' law of suspension, which was discussed in module 3, applies here also. Diameter of the globules, densities of different phases, viscosity of continuous phase, and gravitational force. In addition to that, other characteristics play an important role in kinetic stability of emulsion. Droplet charge load, zeta potential on the surface of the globule. Higher the zeta potential, more repulsion between globules. That means globule will remain separate. Efficiency and quantity of emulsifier. Does the emulsifier cover entire surface? And is it efficiently covering it? Environmental conditions such as temperature. Higher temperature, mobility increases within emulsion and cause separation. Higher agitation and vibration upon storage. Again, mobility of emulsion phases increase and it will cause separation. Dilutions and evaporation during storage will change the composition and will cause breaking of an emulsion.